Yes. So let me recall what we have seen in the first half. We have seen A-infinity algebras, the definition, and some examples mainly from Hochschild cohomology and from minimal models. We have seen that Yoneda algebras have canonical A-infinity algebra structures, minimal A-infinity algebra structures, and we have seen the notion of morphism of A-infinity algebra, which is a non-trivial notion. In particular, the notion of A-infinity isomorphism is non-trivial. And now let's continue with A-infinity categories and then the bar construction and the derived category. So let me jump to the second part. Yes, so the notion of A-infinity category is the multi-object version of an A-infinity algebra. An A-infinity category is given, first of all, by a class of objects. Then for each pair of objects, we are given a graded morphism space. And we are given composition laws Mn as for an A-infinity algebra, only that now each tensor vector is a space of morphisms between two objects. And these, as in the case of algebras, are homogeneous of degree 2 minus n, defined for n greater or equal to 1. And they satisfy exactly the same A-infinity equations, same infinite system of quadratic relations, but now instead of being morphisms from a tensor n to A, they are morphisms from this tensor product of morphism spaces to ax0, xn, but formally it is exactly the same equation. And again, we can take homology. If we take homology, then the homology of A becomes what we could call a category without identities, and it's a category enriched in graded vector spaces. H star of each of these complexes is a graded vector space, and M2 will induce an associative composition, which makes this then into a category, but without identities, since I did not assume that there are identities. And then as an exercise, you can define A-infinity functors by taking the definition of an A-infinity morphism between A-infinity algebras and passing from one object to several objects. Then we have the notion of homologically unital A-infinity category. This, by definition, holds if the homology category has identities. This is perhaps the simplest definition of possible definition of unitality. Then if we have a homologically unital A-infinity category, which is concentrated in degree 0, so we assume that all these morphism complexes are just concentrated in degree 0, then this is exactly the same as a K category, a category whose morphism sets are endowed with vector space structures such that the composition is bilinear. And then a homologically unital functor is the same as just a K linear functor. Now we look at A-infinity functors between homologically unital A-infinity categories. And we say that such a functor is a quasi-equivalence if its first component induces quasi-isomorphisms in the morphism spaces, morphism complexes, for all objects x and y. And so this is the quasi-fully faithfulness. And then we also require H0 of F to be an equivalence of ordinary K categories. This is the good notion of the equivalence between homologically universal A infinity categories. So again, if we consider the case where both categories are concentrated in degree 0, then a quasi-equivalence just reduces to an equivalence of K categories. Okay, now in the next section, I will use the bar construction to reformulate the definitions of A infinity algebra and A infinity algebra morphisms in a compact way, and especially without any signs. And then I will use this setup given by the bar construction to define homotopy in a compact way. Okay, for this, some preparations are needed for the bar construction. So for a graded vector space V, we define the reduced tensor co-algebra as the following vector space. Well, it's just the sum of all the strictly positive tensor powers of V. Yes. I mean, if we could also take K plus this, and then instead of T bar, we would just write T, and it would be the tensor coalgebra. But the reduced tensor coalgebra does not have this K. The zeroth power does not occur. And well, it's a coalgebra. We define the deconcatenation coproduct. Well, if we have a tensor denoted by, well, a sequence with commas instead of tensors in order to reduce the possibility for confusion. So if we have such a tensor, then the co-multiplication cuts it into two in all possible ways and takes the sum. And in particular, if we just have a tensor of length 1, then by definition, its deconcatenation vanishes. Its coproduct vanishes. And if we have a tensor of two factors, V1 tensor V2, then its deconcatenation is V1 tensor V2 in this tensor product of reduced tensor coalgebras. Now this tensor coalgebra has a nice finiteness property, if you like. The co-multiplication is locally finite in the sense that if we take some fixed element and apply the iterated co-multiplication to it, then after finitely many iterations, we will find 0. Yes. So yeah, if this element doesn't involve more than n factors, then the n plus first iterated co-multiplication will kill this element. And we say that it is co-complete. It is analogous, it is kind of dual to the behavior of the maximal ideal in a complete local commutative algebra. And so this algebra is co-complete, and it comes with a canonical projection onto V. And this projection is universal among all graded morphisms from a co-complete coalgebra 2v. Okay, so we have this universal property. We take a co-complete co-algebra in the category of graded vector spaces, and we look at a linear graded map to our graded vector space V. And this linear graded map extends lifts in a unique way to a graded co-algebra morphism with target the reduced tensor co-algebra. Or put differently, if we have such a co-algebra morphism, it is uniquely determined by its composition with the projection onto V. Yeah, this looks a bit confusing, but it is just the dual of the usual universal property of the tensor algebra, of the reduced tensor algebra. Yes, so the reduced tensor algebra is the same vector space, but with the concatenation product. And it has the dual property, yes, whenever we give ourselves a linear map from V to some non-unital algebra, it extends in a unique way to an algebra morphism defined on the tensor algebra on V. Yes, so this is, of course, the natural universal property, which we know very well for the tensor algebra. And you just take this property and reverse the arrows, then you get this property. Yes, instead of the inclusion of the generators, we have the projection onto the co-generators. Now for a tensor algebra, we also have such a universal property for derivations. Yes, if we give ourselves a linear map from V to this DG algebra, to this algebra, graded algebra, for any linear map to this algebra, we can find a unique derivation of the tensor co-algebra extending this linear map. Okay, that's well known and easy to check. And we have a dual property for the reduced tensor co-algebra. Yes, whenever we give ourselves a graded map defined on the co-algebra with values in V, graded of degree E, it uniquely lifts to a co-derivation of the tensor co-algebra. Co-derivation means that we have this equality, yes, which is just the dual of the equality characterizing derivations. And yes, so given this V from TV to V, we can lift it to a derivation from T bar V to T bar V, and we can make this explicit, and namely, well, it has components. Yes, if we take V, the nth tensor power of V on the left, it is mapped to the uth tensor power of V on the right by this formula. As you can easily check, if we, yeah, this is, we get this formula just from the universal property. And then in this way, we get a bijection between co-derivations of degree E of the reduced tensor co-algebra and the elements in the component of degree E in the morphism complex from, in the morphism graded space from the reduced tensor co-algebra to V. Okay, and now, yeah, so this is very nice already. So this will allow us to transform the MNs into certain BNs, which will fit together to form a co-derivation. And now we also want to get rid of the signs. So here is what we do to get rid of the signs. So let's take A to be a graded space. We write sigma A as always for its shift by 1 degree. And we have a canonical map, yes, of canonical isomorphism of degree -1, which at the level of vector spaces is just the identity. So it changes the degree of this element by 1. And now we get a bijection between graded linear maps of degree 1 from the nth tensor power of sigma A to sigma A, and graded linear maps of degree 2 minus n from the nth tensor power of A to A in this way. Yes. So on the one hand, we have, let's say here we have a map Bn of degree +1 from the nth tensor power of sigma A to sigma A. So this is of degree +1. Then we can compose it with this, the nth tensor power of this canonical map. So this S is of degree -1, so its nth tensor power is of degree -n. The composition will be of degree 1 minus n. On the other hand, we can look at this morphism of degree -1, and then we can compose all this. And then, -n plus 1, and in this direction +1, the sum of these three contributions is 2 minus n. So this corresponds to a map Mn. And we require this square to be commutative. In this way, we establish this bijection between maps Mn and maps Bn. And here there is a choice. Yes, we require this square to be commutative. We could also, for example, require it to be anti-commutative, or we could require it to be commutative or anti-commutative according to the parity of n. So we have at least 3 possible conventions, and this leads to at least 3 possible conventions for the sign in the definition of the A infinity structure. And there are papers in using these 3. There are different papers, each of them using different conventions. So the different conventions come from the choice in this sign, which we use to translate between Bn's and Mn's. But in all conventions for the Bn's, we will not have any signs. So here we have the corresponding lemma. Yes. So we have maps Mn defining an A infinity structure. These correspond to maps Bn, and the maps Bn together yield a co-derivation. And this we have an A infinity structure satisfying the A infinity equations if and only if this co-derivation is differential, if and only if its square vanishes. And if you decode this, then you get these equations for the Bn's, yes, using this expression for the map from the nth to the uth tensor component. You see that we get this family of equations for the Bn's, and the nice thing now is that we have no signs at all. Yeah. Of course, if we apply this to elements, then the causal signs will appear, but in this expression, no signs appear. And now, this is the compact way of encoding an A infinity structure on A. And by definition, the reduced bar construction of an A infinity algebra A with multiplications mn is the reduced tensor coalgebra on the suspension of this space together with the B's obtained from this bijection between mn's and bn's. Okay, and then you can, so we have encoded all the mn's in a very compact way in this differential of the reduced bar construction. And then you can check that the complicated definition of morphisms of A-infinity algebras reduces to the very simple definition of morphisms of differential graded coalgebras. So we look again. We look at morphisms of differential graded coalgebras between these two reduced bar constructions, and they are in bijection with these families. And again, well, the bijection is given by taking such a morphism here and composing with the projection onto sigma A prime, projection onto the co-generators. In this way, from this morphism of DG coalgebras, we get a family of linear maps, which then translates into the family on the left. And the A-infinity equations on the left simply come from the fact that this morphism should be compatible with the differentials of these two DG coalgebras. Right, and now we can use this bijection to define homotopies. Let's take two A-infinity morphisms between A-infinity algebras. Then we have the corresponding morphisms of DG coalgebras, and we define a homotopy between such morphisms of DG coalgebras to be a graded morphism of degree -1, since it should be a homotopy, which satisfies this co-derivation condition. Yes, one could call it an FG co-derivation. And well, it's a homotopy from F to G, so its boundary, just the boundary in the morphism complex. Yes, these are in particular complexes, so this becomes a complex. We take its boundary, in other words, the graded commutator with the B's. This should be the difference F minus G. Okay, so in this way, we define homotopy between the associated morphisms between DG coalgebras, and then you can translate this notion of homotopy again into the notion into the language of families of graded maps defined for n greater or equal to 1 of degree -n instead of 1 minus n, which have to satisfy certain conditions with respect to F minus G. Okay, this is not hard. And then the somehow surprising theorem is that homotopy gives us an equivalence relation on the space of, on the set of A-infinity algebra morphisms from A to A prime, which is compatible with composition on the left and on the right. Yes, this is yes, not obvious at all. And then, perhaps even more surprising, if we have a morphism of A-infinity algebras, it is a quasi-isomorphism. Yes, remember that this means that its first component is a quasi-isomorphism of the underlying complexes. It's a quasi-isomorphism if and only if it becomes invertible in the homotopy category of A-infinity algebras. So we take the category of A-infinity algebras and we divide by the homotopy relation as defined in the first point. Yes. And this is this is of course something surprising if you're used to working with DG algebras. If you have a quasi-isomorphism of DG algebras, it has no reason to become invertible up to any type of homotopy relation. And also, I mean, one can define a homotopy relation on the space of morphisms between two DG algebras, similarly to this. But this relation will not be an equivalence relation unless the source DG algebra is, well, cofibrant in a suitable modeled structure. Okay, but for A-infinity algebras, we have this strong theorem: quasi-isomorphism and homotopy equivalence are the same thing. Okay, and this also extends from algebras to A-infinity categories, where quasi-equivalences replace quasi-isomorphisms. And one can show that if we take the category of DG categories and localize with respect to quasi-equivalences, it is equivalent to the localization with respect to quasi-equivalences of the category of A-infinity categories, and also therefore to the homotopy category, yes, to the category modulo homotopy of A-infinity categories. Yes. So this is a statement which has been accepted as true for a long time before it was finally formally proved by Gallinacco, Ornaghi, and Stellari in 2019. And they proved this statement at the level of one categories, yes, at the level of the localized categories. Then one can try to refine it and prove it for the associated quasi-categories, infinity one categories. This is a result due to O and Tanaka from 2020. And then one can try to further refine it to an equivalence of infinity two categories. And O and Tanaka had also announced this, but there seems to be a gap. They have retracted the corresponding preprint. So as far as I know, this is not yet clear. Okay, but this is just a remark for people in the know. Yes. Now these are somehow the most fundamental results on A-infinity algebras and the corresponding category up to homotopy and localization with respect to quasi-isomorphisms. Now let's look at A-infinity modules and their derived category. So the reference is the thesis of Kenji, Lefebvre, and Hasegawa, which you can find on the archive. Let's take an A-infinity algebra, and now let us consider the non-reduced bar construction. So we take the reduced bar construction, which we have just defined, and we add a copy of K. So then it becomes an augmented DG co-algebra, as the underlying vector space is just the reduced one plus K. In the co-multiplication, we add U tensor 1 and 1 tensor U at the beginning, at the end. The differential restricted to K vanishes and is the same on the other elements. And now, whenever we have a graded vector space V, we can use it to produce a co-free BA co-module as a graded space, it is just the tensor product, and it has the natural co-multiplication, where we use the co-multiplication of the bar construction like this, yes, dual to the construction of an induced module. And then we define an A infinity module over our A infinity algebra A to be a graded vector space M together with a differential on the induced co-module. As we have M shifted and form the co-free co-module. And on this co-free co-module, we give ourselves a differential, which makes it into a differential graded co-module over BA. And we write BM for this DG co-module. And again, so this is formulated in the compact way using the co-bar construction. You can reformulate it in the language of families. First, families of BMNs, where we have the suspensions, and all the maps are of degree +1, or equivalently in terms of MNs, which are of degree 2 minus n, and satisfy suitable A infinity equations corresponding to the fact that BM square vanishes. And these equations will in particular tell you that if you homology, then the homology of M becomes a graded module over the homology of A. For example, the algebra becomes a module over itself, the free right module of rank 1. And then if A is homologically unital, then we can define M to be homologically unital if its homology is strictly unital over this unital graded algebra. Okay. Then we have the natural notion of morphism, which we can define most quickly using the bar construction, or equivalently using the language of families of graded maps defined for n greater or equal to 1 of degree, let's see, 1 minus n, if I'm not mistaken. Then we have the natural notion of quasi-isomorphism. Such a morphism between A infinity modules is a quasi-isomorphism if F1 is a quasi-isomorphism between the underlying complexes. We have the morphism complex, its nth component is formed by the graded morphisms of degree n, just of graded comodules. And the differential of this complex is defined using the graded commutator with the differentials of M of BL and BM. And in this way, yes, using these complexes of morphisms, we obtain a DG category of A infinity modules in the sense of Professor Chen's lectures yesterday. Two morphisms are homotopic if their classes in H0 are equal. And then we have a theorem analogous to the one for A infinity algebras, but actually easier. A morphism between the A infinity modules is a quasi-isomorphism if and only if it is invertible up to homotopy. So again, quite surprising if one is used to morphisms between DG modules over DG algebras. And the localization of the category of A infinity modules with respect to the class of quasi-isomorphisms is isomorphic to the quotient of this category by the homotopy relation. So there is no if you like, there's no difference between the category up to homotopy and the derived category in the A infinity world. Okay, now to define the derived category, let us suppose that our algebra is homologically unital, and then we use homologically unital A infinity modules, and we invert quasi-isomorphisms, or equivalently, we divide by the homotopy relations to define the infinity derived category of our infinity algebra. And this category is then canonically triangulated. In fact, it is the stable category of a suitable Frobenius category, namely the Frobenius category of co-free DG comodules. And then, well, we have done this in the case of the DG algebra. We can extend the definition to homologically unital A infinity categories, and then instead of free modules, we have to look at representable A infinity modules. Okay, and now suppose that our A infinity algebra is actually concentrated in degree 0, so it's an ordinary unital associative algebra. Then, well, we have a natural inclusion. Every ordinary complex of A modules defines an A infinity module structure, and we get a functor, and this functor is an equivalence. Right. And on the right-hand side, maybe I will do this. On the right-hand side, we have minimal models. I think, yeah, yes, I'm not sure I've said it. Yes, but anyway, as for DG algebras, for DG modules, we also have an analog of Kardashvili's theorem. Up to A infinity quasi-isomorphism, we can replace a DG module M by its homology with an A infinity module structure, which is minimal. The M1 vanishes. So we have the homology of the complex together with higher structure, and as shown by this equivalence, this pair consisting of homology with higher structure determines the complex up to quasi-isomorphism. So this is the positive answer to the first problem, the first motivational problem. Then, well, if we have an A infinity quasi-isomorphism, then it is not hard to define an A infinity restriction functor. Yes, it's not entirely obvious, but it's an easy exercise to define this functor, and this functor will become an equivalence. You can show that this category is compactly generated by the free module of rank 1, as in the case of an ordinary algebra. And we have a Morita theorem if we have an arbitrary compact generator and an A infinity quasi-isomorphic algebra to the endomorphism, the DG endomorphism algebra of this generator. Yes. Defined using the morphism complex, which I have given. The morphism complex defined using DG comodules over the bar construction. Then we get an equivalence between the A infinity derived category of B and the A infinity derived category of A, which maps the free module to the given generator. We get an A infinity Morita theorem. Yes, and here, sorry, here I say it, yes, what I already said orally. So each A infinity module also admits a minimal A infinity model whose graded space is just the homology of M. And if we combine this fact with this equivalence, then we get the solution to the motivating problem of recovering the complex up to quasi-isomorphism from its homology with a minimal A infinity structure. Then the theorem, this theorem on derived category, is also extends from A infinity algebras to A infinity categories. And we just have to replace the single compact generator A by the family of compact generators given by the representable A infinity modules. And we have to replace A infinity quasi-isomorphism in this statement by A infinity quasi-equivalence between the corresponding categories. And this is the end of this lecture. So we see that things are quite similar. In summary, things are quite similar to what is going on for DG algebras, DG modules, and DG categories. So the overall behavior is similar. The theory is similar, but we have strong theorems which allow us to construct inverses up to homotopy for all quasi-isomorphisms. And also, well, we have more computational tools, which I have not had the time to illustrate here, but which are really very useful and very important for computations. And I'd like to end here. Thank you very much.
Well, thank you, Bernhard, for your very nice talk. Are there any questions or comments?
Can I ask a naive question, maybe?
Yes, please.
Maybe I missed some part of the talk, but assume that K is a commutative ring. So we know that CdG of K is a typical example of a non-trivial DG category. Yes?
Sorry, K is a field. K was a field. K was a field for simplicity, but some parts of the theory carry over to commutative ground rings.
Yes. I mean, CdG of K is a typical example of a non-trivial DG category. Yes?
Right.
Do we have a similar example for A infinity category? I mean, non-trivial, non-example of A infinity category?
I would say it is the same. Yes. I mean, K is an associative algebra. It is in particular an A infinity algebra. And well, since it's concentrated in degree 0,
yes,
its category of A infinity modules is the same as its category of complexes. Yes.
So it's somehow trivial. Yes.
Yes. Yes, if you like. Yes. 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 Yeah. Yeah. Yes. Yeah. Yes. This basic category remains the same in both cases. Yes.
Question, comments?
Let me see. Is there a question in the chat? No.
There is no question. So let's thank Bernhard and again. Thank you very much, Bernhard.
Thank you very much.
And